Good afternoon, class. We are looking at section 4.4, optimization problems. So we have differentiation formulas, as discussed before. Extreme or local max, local mean, absolute max, absolute mean, definition of a critical point, and how to find absolute max and mean using the closed interval theorem. How derivatives affect the shape of a graph. A function is increasing when f prime is positive, decreasing when it's negative. A critical point refers to where f prime is 0 or doesn't exist. A relative max or relative mean is where the critical point happens at the top or bottom of an interval of a graph. F double prime is positive means f prime is increasing and it's concave up. If f double prime is negative means f prime is decreasing, it's concave down. And where f double prime is 0 or doesn't exist would be possible location of inflection points. So let's look at the optimization problems. Optimization problem is the problem of finding the best solution from all feasible solutions. In other words, find a solution in the feasible region which has the minimum or maximum value of the objective function. Examples would be maximizing profit, minimizing cost, maximizing area enclosed, etc. This is known as the first derivative test for absolute extreme values. And what it says is basically when we go through the first derivative test or even a second derivative test, if we happen to have one critical point, it is not only a local extremum, it is also an absolute. So the synopsis of what's happening with the first derivative test or even the second derivative test. A local extremum is an absolute one if it is the one and only one extremum. Normally we deal with an open interval also. So open. Interval, because if it's closed, you have to check the endpoints as well. So to get us started with this concept, a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? We can make something up such that the fencing add up to 2,400 and calculate the area for each case. For example, in this case, the width is 100, the length is 2,200, gives us the area of 22,000 square feet. This one is 700 versus 1,000 gives us 700,000 square feet. This one 1,400. Their product is 400,000 square feet. But how do you make sure it is absolutely the maximum area you're looking for? We tackle it in the following manner. Let the width be X, the length be Y, and along the river, we don't need that. So there are two things we are interested in. Number one, the objective function. What is our objective? Largest area. So the area is X times Y, the width times the length. So that's what we want to achieve. What is the constraint? What is the limiting factor? The limiting factor is that we have only 2,400 feet of fencing. So the constraint function becomes this. We have X times 2, and then Y normally is 2Y but on this side, we don't need it. So 2x plus y must be 2400. So far, all we have done is translation into math. A is a function of two variables, x and y. So we always use the constraint to solve for one of the variables. In this case, we're going to solve for y, 2400 minus 2x. And we're going to replace the y. And when we do that, a, which is a function of two variables, x and y, becomes a function of one variable, namely x. We need to know the domain. Domain on this, x represents dimensions. It must be positive. And also, if we set this one equal to 0, this results in x equals 1200. So if you choose a number larger than 1200, the parentheses become negative, the area becomes negative. It's not doable. So your domain is 0 to 1200. That's an open interval of 0 to 1200. We want to maximize this. So we are going to take a derivative. A prime of x is 2400 minus 4x. And we set it equal to 0 to find CPs, critical points. And x becomes 600. So what do we have? We have only one critical point. We have an open interval. This is an open interval. So when we go through the process, if this is going to maximize the function, then it will be an absolute max. If it's going to minimize, it's going to be an absolute min. I'm going to look at both the first as well as the second derivative test because you have to know how to do both. So if we go with the first derivative test, we need a sine graph. So here's the sine graph. You put the CP here, 600. This is x. This is a prime of x. And to the left of 600, you pick a test point. Any number will do. So TP. Now, for testing, you can even use 0, although 0 is not in the domain. So you can use 1. And to the right of it, let's say, I don't know, 1000. So those are TPs. If you plug in 1 or even 0 into a prime, makes it positive. And if you plug in 1000, 2400 minus 4000 makes it negative. So increasing, decreasing, that proves we have a local max at 600. And of course, we said because it's an open interval and there is only one critical point, it is also an absolute max. What about the second method, namely second derivative test? So if I take the second derivative, I get minus 4. And remember, we have to plug in 600 and observe to see whether it's positive or negative. This will always be negative regardless because it is not a function of x. Therefore, it gives us a maximum. Why is that? Because when it's negative, means it's concave down, looking like that. And therefore, the maximum occurs at that point. So x equals 600 gives us the maximum. We can put it into this or this function to find the missing y, becomes 1200, and of course 1200 feet. So the dimensions are 600 by 1200, and the area is the product of the two, which is 720,000 square feet. We want to find two numbers whose sum is 80 and whose product is a maximum. So first and foremost, let's define our variables, two numbers, X and Y. You always have to define your variables. What is our objective? We want the product to be maximum. So maximize the product of X and Y. What is the limiting factor? What is the constraint? The sum must be 80. So X and Y, they add up to 80. That is the constraint. When we look at the objective function, it's a function of two variables, namely X and Y. We are going to solve for Y here, which makes it 80 minus X. Replace the Y here with 80 minus X, and the P becomes a function of X. First, notice instead of just P, I'm going to write P of X because this was a function of two variables. X times 80 minus X, and if you distribute, you get 80X minus X squared. This is for the next part when we're going to differentiate. So what is the domain? What are we trying to achieve? We want to get the maximum. So because we want to have a maximum product, we are hoping not to get a zero or a negative number for that matter. We are hoping to get a positive value. Therefore, X must be positive and can't be zero. And what about this one? If you set this one equal to 0, X becomes 80. So if you choose a number larger than 80, it becomes negative. The product is negative. Therefore, X is between 0 and 80. So one more time. The product of these two pieces, we want them to be maximum. So we are hoping not to get a 0, not to get a negative number. Since we don't want this to be 0, X is larger than 0. What about negative? If you set this one equal to 0, X is 80, and if you choose a number larger than 80, makes this parentheses negative, the product of these two becomes negative. The next step is taking the derivative. P prime of X is 80 minus 2X and set it equal to 0 to find the CP, or the critical point of X equals 4. Notice we have the open interval of 0 to 80. We can represent it, and this is an element of that as 0, 8. This is one way to write. So is this going to maximize or minimize? We are going to go with the second derivative since it's easy, and P double prime becomes negative 2. You have to plug in 40. This is not a function of X, makes no difference. Negative results in max, again, because when it's negative, it means it's concave down, looking like that. Maximum appears here. So if X is 40, then we go either to this one or this one. Y also becomes 40, and their product is 1600. A farmer with 240 feet of fencing wants to build an E-shaped enclosure besides a creek, as seen in the diagram. Find the maximum area that can be enclosed. So again, we have the dimensions, the width, we call it X, the length, we call it Y. So what is our objective? Is to maximize the area, which is X times Y. What is the constraint? What is the limiting factor? We have only 240 feet of fencing. So can anybody give me the equation of a constraint, therefore? We have 240 feet of fencing. 1, 2, 3x. Normally we have 1 and 2y, but this side doesn't need it. So 3x plus y must be 240. Again, a is a function of two variables. We are going to solve in the constraint equation for y, 240 minus 3x, and replace the y with that such that a becomes a function of x. Again, this is a function of two variables, x and y. Now, when we do the replacement, becomes a function of x only. Let's discuss the domain again. Dimensions must be positive, so x must be positive. If you set this one equal to 0, 240 equals 3x and x becomes 80. If you pick a number larger than 80, the parenthesis goes to negative, the product is negative, the area becomes negative, and that's why x is between 0 and 80. We're going to distribute, and we get 240x minus 3x squared. And now calculus starts. Remember, there's only one step of calculus. A prime of x is 240 minus 6x. We set this equal to 0. This is the only calculus step. For now. So set equal to 0, x becomes 40. So let's look at what we have. We have an open interval of 0 to 80. And we have a 1 CP, one critical point. So whether it's going to maximize or minimize, it's not local, it is also absolute. So again, it's easier to go with the second derivative. That's another step in calculus. So if we go with second derivative, we get minus 6. Negative means concave down, means maximum. So first, this is another step of calculus. Then negative means concave down, looking like that. Maximum occurs at x equals 40. Now you can go to this formula or this formula to find the other variable y. So 240 minus 3 times 40 makes it 120. So the dimensions are 40 by 120. And the area is the product of the two numbers, 4,800 square feet. By the way, this can be anywhere, even somewhere to the right or left, doesn't have to even be in the middle, in case. That gives you the same area. A box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimensions that minimizes the amount of material used. Because of the cost, perhaps, we want to minimize the amount of material. So first, I want to give you a piece of information and remind you of what we have learned in algebra geometry. This is called a rectangular solid. If I want to find the volume, I'm going to multiply the width times the length times the height. If I want the surface area, meaning if I want to gift wrap it, that's the concept of a surface area. The front face is the length times the height. I have two of them. The side is width times the height. I have two of them. And the base is length times the width. I have two of them. So surface area is 2 times W times L plus H times L plus H times W. If it's a cube, means all sides are equal, then the volume would be the width times the length times the height are all the same, so S cubed. The surface area, one face has an area of S squared. There are 6 of them that are identical, 6S squared. So going back to the question, we want the dimension that minimizes what? The amount of material used, gift wrapping. So the wall, this is X times H, and the walls, there are 4 of them, 4 times X, H, they're identical. The base is X squared. There are 2 of them, is 2X squared. However, since it's open top, it's just 1X squared. So the surface area is 4XH plus X squared. We are going to minimize that. So again, why is it X squared and not 2X squared? Because it's an open top, otherwise it's 2X squared. What is the limiting factor? It's subject to constraint. The volume must be 32,000 cubic centimeters. The volume is X times H or X squared H. So subject to constraint, being the volume equals X squared H equals 32,000. We always use the constraint to solve for one of the variables. We have 2 variables, X and H. We want to get rid of the H, so we're going to solve for H by dividing by X squared. We will put that in here. So 4X times the new H plus X squared. S, we're going to change the name to S of X, which means now it's a function of X. So 4 times 32,000 is 128,000. This X goes away, this becomes X. So it's important to see that this is going to go away and this changes to X. So that's what we have. Now, if we take, for the sake of the next section, next part, which we are going to differentiate, we can rewrite this as 128,000 X to the power of -1. And the reason X is positive is an open interval of 0 to infinity, because X represents dimensions, must be positive. There is no other factor to look at here except X has to be positive, and it can't be negative, it can't be 0 either. So far, we've done algebra, geometry, you name it, and now we're going to get to calculus by taking the derivative S prime of X. And the reason we went this route for the sake of differentiation, 128,000 times -1 makes it -128,000 X to the power of -2 plus 2X. Remember what we are looking for, CPs. That means we want to see where the function is 0, when the function does not exist. And the way it is hard to see. So if you notice, this is -128,000 over X squared. So if you write this over X squared and take a common denominator of X squared, you get to this answer. So this is the only calculus step. This is algebra so far. S prime equals 0, the top is 0. We're going to work on it. S prime doesn't exist, the bottom is 0. The bottom is 0 gives you X equals 0, but X cannot be 0 because it's an open interval, 0 is not included. So let's look at S prime equal to 0 by setting the numerator equal to 0. When we do that, we get 2X cubed equals 128,000. X cubed is 64,000. And when you take a cube root, you get 40, and the units are centimeters. So what do we have here? One critical point and open interval. So whenever we're done figuring out whether it's max or mean, it's an absolute. So we can do the first derivative test, which requires a sign graph, or we can do S double prime using this, minus 128,000 times negative 2, makes it positive 256,000 x to the power of negative 3, and this is plus 2. Now, how do you do the second derivative test? You must evaluate S double prime, and this is the second calculus step. So first calculus step, second calculus step. Now evaluated with the 40. By the way, this is 256,000 divided by x cubed. So if I plug in 40, it's 256,000 divided by 40 cubed. But I don't have to even evaluate it. It's positive because the numerator is positive. So is the denominator. Plus 2 is even more positive. So you have to recognize S double prime evaluated at 40 is positive, which means minimum. Why again? Because when it's positive, means concave up, looking like that. And that's why it's the minimum. So if X is a 40 and that gives us the minimum we are looking for, what is H? You can go to this formula or to this formula, 32,000 divided by 40 squared, which is 16,000, 1,600, and it makes it 20 centimeters. So X equals 40, H equals 20. So it's 40 by 40 by 20. Now, we want the dimensions and we are done. But if they ask what is the surface area now, we're going to plug in. We're going to replace the X with 40, H with 20 into this, and it results in 4,800 centimeters squared. So as you can see, there is a lot of algebra and geometry involved, but again, 1 and 2 steps of calculus, very simple. We want to find two numbers whose difference is 18 and whose product is a minimum. So first, let's define those. What are those numbers? X and Y. Choose any variable you like. The difference is 18. X minus Y is 18. The product is minimum. So the objective is to minimize the product, which is X times Y. And the constraint is that we know the difference is 18. So X minus Y is 18. By the way, you could write Y minus X equals 18 and the numbers just switch, that's all. As always, we look at the objective function, we see two variables. So we use the constraint to solve for one of them. If I move the 18 here, becomes X minus 18. I move this one, becomes Y. So Y is X minus 18. If I replace the Y with that, now P becomes a function of X. Now, a couple of things. Number one, we are replacing the Y with X minus 18. Number two, when we multiplied, when we distributed, we get X squared minus 18X. Number three, the domain is all real numbers. We want to see why this is the case. We want to discuss the domain. What is the objective? Minimize the product. If I want to minimize this two, if I get 0 is okay. If I get negative, it's even better because 0 is less than any positive value. and negative is less than 0. So since we are minimizing, we can use any numbers. There is no restriction. Okay, again, because we are minimizing the product of these two numbers. Let's go with p prime, which makes it 2x minus 18, set it equal to 0 to find CPs, critical points. There is only one of them, x equals 9. So we have an open interval of negative to positive infinity. We have one critical point. The reason open is important because if it's closed, you have to evaluate it at the end points as well as the critical point, okay? There's only one critical point, open interval, so whenever we're done, it's not only local, it's also absolute. So again, the second derivative makes it easy because p double prime is just number 2, a positive value, which makes it minimum. Why is that? Again, because when it's positive, means concave up, looking like that. And we have the minimum at x equals 9. Now, we put this either into this or that, makes no difference, and gives us the other number, y is negative 9. Again, I want to go back to this. If you wrote y minus x equals 18, then these two interchange, not a big deal. Still, you get the same two numbers in a different order. And what is their minimum product? Minus 81. Could somebody read this question, please?
I can read it.
Please.
Let us enclose a rectangular area of 288 feet squared and then divide it into 3 equal sized pens with parallel sides. What dimensions will minimize the material needed?
Excellent. So what is the objective? We want to minimize the material. Well, this is x. So we have 1, 2, 3, 4 of them. This is y. We need 2 of them. So we want to minimize the perimeter, if you will, which is 4x plus 2y. So again, this is x. We have 1, 2, 3, 4 of them. This is y. We have 2 of them. And it's subject to a constraint. What is the limiting factor? The area must be 288 square feet. And we know the area is the width x times the length y. So area is x times y equals 288. So this is in essence translation of the question. Again, the objective function has two variables. So we go to the constraint and we solve for y becomes 288 over x. We are going to change this y to 288 over x. So replace the y with 288 over x. This is 4x. The product of these two is 576 over x, 576 over x. And the reason I'm going to put x to the power of -1 is for the sake of the next part when we want to differentiate. But what could x be? X must be positive. Why is that? Because dimensions cannot be negative. And we have the open interval. Open interval of 0 to infinity. So we're going to differentiate, and it's easier to differentiate it with respect to this setup. P prime becomes a 4 plus the product of these two is minus 576 and x to the power of -2. Remember, we are looking for CPs. critical points. So let's put this underneath. Let's take a common denominator of x squared. So this becomes 4x squared minus 576 over x squared. Now, a rational expression, a fractional expression is 0 when the top is 0. It's undefined or doesn't exist when the bottom is 0. The bottom is 0, that means x is 0, and 0, remember, is not in the domain because it's an open interval. So we set the numerator equal to 0. That means four x squared is 576. Divide by 4, 144. There are two answers, and the only acceptable answer is positive because of the dimension. So we have an open interval with one critical point. So whenever we are done with the result, it's not only local, it is also absolute. So this was one calculus step. The next one is p double prime, and we're going to go to this and differentiate it because it's easier than the other two. So 4 gives you 0, then minus 576 times negative 2. The product of these two gives us 1,152, x to the power of negative 3. So again, the only calculus steps are this one and this one. I'm going to rewrite this as 1152 over x cubed. And the second derivative test says evaluate this when x is 12. So if I put 12 here, 1152 over 12 cubed, you don't even have to know the answer, but for sure it's positive because the numerator and the denominator are both positive. So when p double prime is positive, that means it's concave up. That means the minimum occurs. So that means concave up, looking like this, and the minimum occurs at x equals 12. So let's go back to either this or this expression to find the missing y. 288 divided by 12 is 24 feet. So the dimensions are x is 12, y is 24. If somebody, so the dimensions we found and we are done, but if somebody says what is the minimum amount, that means in this formula replace the x with 12, 4 times 12, and 2 times 24, and they add up to 48 plus 48 is 96 feet. So again, in this formula, we replace the x and y with 12 and 24. Could somebody read this, please?
I'll read it.
Please.
From a thin piece of cardboard, 8-inch by 8-inch, square corners are cut out so that the sides can be folded up to make a box. What dimensions will yield a box of maximum volume? What is the maximum volume?
Perfect. So the diagram and drawing makes it very important. So this is the piece of cardboard. We're going to cut X amount on each corner. We're going to fold it up and it looks like this. It was originally 8 by 8. So this side becomes 8. We are cutting X from each side. So 8 minus 2X, 8 minus 2X, and the height is X. So the objective is to maximize the volume, which has, generally speaking, the formula, the length times the width times the height. And the constraint is that we know the width is equal to the length, 8 minus 2x, and the height is x. That would be the constraint according to the cutting that we did. Therefore, the formula becomes x times 8 minus 2x quantity squared. And remember, x must be positive because it's a dimension. Also, when we write that, x must be less than 4. The question is why? Let's look at the reason for that. So x must be positive because it represents dimensions. Why is it less than 4? Take a look at this piece, 8 minus 2x. If you set it equal to 0, x becomes 4. So if you choose x to be larger than 4, or even 4, at 4, the volume becomes 0. If it's more than that, becomes negative. In essence, you can't cut this in half. It doesn't create a volume for us. All right, so that creates this open interval of 0 to 4. Now we're going to rewrite this. First, we want to square this. So let me just write the square of that using a minus b quantity squared. So this gives you 64 minus 2 times 8 times 2 minus 32x plus 2x squared is 4x squared. Now, this is what we get. We are going to multiply this by x. So we get 64x minus 32x squared plus 4x cubed. We put this in a descending order. So 8 minus 2x quantity squared is this, multiplied by x, and put it in descending order. Now let's do calculus. V prime, because we are looking for critical points, is 12x squared minus 64x plus 64. Now, we want to set this equal to 0 and solve. Let's factor the common factor or the GCF as follows. Can take the 4 out. I get 3x squared minus 16x plus 16. You can do the factoring, and you end up with 3x minus 4 times x minus 4. And it's really not too bad because this number 3 is a prime number, right? So it's 1 and 3. Then all you have to do work on this number. The 16 can be 1 and 16, 2 and 8, 4 and 4. You figure out what will work out. So there are, if you set this equal to 0, there are 4 critical points. When you set this one equal to 0, x is 4/3. And you set this one equal to 0, x is 4. So there are 2 critical points. And you go back to this, you see that 4 can't be, so this is out, simply because the domain is an open interval of 0 to 4. So there is an open interval with 1 critical point. So this is going to be not only local, also absolute. So what do? We have a choice. Do the sign graph with 4/3 for V prime, or find V double prime. So if we use this one, V double prime is 24x minus 64. And we're going to plug in 4/3. So 24 times 4/3 minus 64. We have to evaluate it. So pay attention to this. This has to be evaluated because all we want is the sign, negative or positive. Notice what happens. I can drop this and change this to 8. 8 times 4 becomes 32. Minus 64 is negative 32. Means concave down, means maximum. Negative 32 means concave down, means maximum occurs at x equals 4/3. So if x equals 4/3, which is the height, what is the length? 8 minus 2 times 4/3. 8 minus 8/3. And it becomes 16/3 because 8 is 24/3, everybody. So the dimensions are 4/3 by 16/3 by 16/3. What is the volume? If you multiply them through, you get 10^24/27 or 37 and 25/27 cubic inches. This is the precise answer using fractions, multiplying these numbers. 4 by 16 by 16, you get 10^24. 3 by 3 by 3, you get 27. So that's the exact answer. They may ask for an approximation using decimals. You can do that. Here's the last question. Could somebody read the last question, please? Wow. A stereo manufacturer determines that in order to sell X units of a new stereo, the price per unit is supposed to be 1,000 minus X. The manufacturer also determines that the total cost of producing X units is given by C of X is 3,000 plus 20X. We want to find the total revenue. Revenue by definition is the number of units times the price. Number of units is X. The price, lowercase p. So we are going to replace it with 1,000 minus X. Their product is 1,000X minus X squared. (1,000X minus X squared). We want to find the profit. Profit by definition is the revenue minus cost. Revenue minus cost. So 1,000X minus X squared minus the cost that was given here. So this is minus 3,000 minus 20X. We can put these two together, and to put it in descending order, we get minus X squared plus 980X minus 3,000. So that's the profit function. How many units must the company produce and sell in order to maximize profit? We are going to take the derivative of the profit function P of X. And we take the derivative here, we get minus 2X plus 980. And to find the critical point, we set it equal to 0. When we set this equal to 0, critical point of X equals 490. Now notice we are producing more than 0. So in essence, the domain is 0 to infinity. And we have only one critical point, although you can always plug in 0 if you think 0 is feasible, and it could be. So x equals 490. Is this going to maximize or minimize? We are going to do the second derivative test. P double prime is -2, which is negative. And that means it's concave down. In that vicinity, looking like that, gives us the maximum. So what is the maximum profit? Here's the profit function. Replace the x with 490. So minus 490 squared plus 980 times 490 minus 3000. When you do the math, it gives you the maximum profit of $237,100. What price per unit must be charged in order to make this maximum profit? You go back to the price function. Price function was 1,000 minus X. So 1,000 minus X, which is 490. And now we get $510. $510 will maximize the profit if we sell each unit for $510.